see whether, yeah, so there are several people, and usually what are trying to prioritize people but potentially the person is really good. You should really start.
Yeah, I don't know too much about this. I know
Exactly. So opportunity to get to know people and also to be familiar prediction. You know, one thing that we really like most of the people nearby.
We collaborated with a lot of people.
So he was at UC for a while.
Oh, really?
Before the ICT.
Oh, cool. That's the creative technologies.
Yeah,
it seems like that's a lot of really interesting stuff.
Totally.
Also, one thing I wanted to do, but I never get a chance to do is getting in contact with ICT people. Many people work on creative design. Yeah, it's big. There are It's actually, that's one
of a lot of work with central system.
I made a mistake. I made a big mistake for today. Wait. They caught me.
Yeah. You started.
Yeah, I graduated from university, Special Institute of Technology.
I just upload extra school grades, the grade results.
And then homework too will come soon. Yeah, I know.
I mean, I didn't do that.
Maybe you try to ask other. Yes, we do have 5 TAs.
No, we have 3 TAs.
Yeah, German has 3. I don't know whether
My dad's side of the family, I guess they lived in Russia a little bit, and then they stayed there, but originally somewhere in Germany. It's been back so far that we're not sure exactly.
That's true. You gotta change.
there were quite a few German settlers, but then later was Russia.
I guess they left kind of early, but I'm not sure exactly when they moved over.
Just like reach for their life.
I think way more than one to
Hi everyone. Hello. So I'm gonna raise hand for 3 seconds. And that's weird. So today we have Daniel Fried, who is a PhD student at UC Berkeley, working with Dan Klein on grounded semantics and structured prediction in natural language processing. Previously, he received a bachelor from University of Arizona and a master from the University of Cambridge. So welcome our speaker.
Thank you. So thanks for having me. Thanks so much, everyone, for coming. And I'll be talking today about systems that interact with people and ground the meaning of language in different properties of the world. And we'll be focusing on pragmatics, so reasoning about world context and reasoning about how this context affects the meaning of language. So this is work with a lot of great collaborators: Jacob Andreas, Rongheng Hu, Volkan Sirik, Anna Rohrbach, LP Morency, Taylor Berg Kirkpatrick, Kate Senko, Trevor Darrell, and my advisor, Dan Klein. So the plan for today is I want to start off by introducing the instruction, interpretation, and generation tasks that we're interested in simple environments, and talk about the standard models that people use for these tasks, which we'll build on. So these models have some interesting failures where they'll have trouble generalizing to new contexts and making correct decisions under ambiguity. Then we'll talk about how a simple pragmatic reasoning procedure can be added on top of these existing models that will fix some of these mistakes and improve both interpretation and generation. And then finally, we'll talk about making this work in real world environments. So following instructions to navigate through houses and office buildings. And I'd like to have this be interactive, so please let me know if you have questions as I go. So let's start off with talking about interpreting and generating instructions. So let's start with instruction following. And as a running example, imagine that you're this robot who's been placed in this house and someone gives you a direction to carry out, like go forward to the bare concrete hall. And you'll have these pieces of furniture in different colored hallways and walls that you'll see as you take actions in the world. So taking one action at a time, you go forward and you predict to stop at this intersection with this bare concrete hall. And this is the correct end destination that the person giving this direction had in mind. So this is a pretty specific direction. It's easy to get it right, but later on we'll see some more ambiguous ones that are difficult to deal with. We're also interested in the inverse task. So
could have just gone one step forward, right? Alternatively, or?
Yeah, so the model's predicting these actions one at a time. And another option it could have taken was to just take one step forward and then predict to stop before reaching any of these objects. Yeah, so we're also interested in the inverse task of you're given a route through the environment and then you want to produce a description of it in natural language that someone else could carry out correctly. So for example, saying go forward to the bare concrete hall. So we'll have a listener model that takes in an instruction and is situated in the environment and then needs to carry out a sequence of actions. And we'll have a speaker model which performs the inverse task, describing a sequence of actions in context. And we'll be working with data-driven models, so we'll have human annotations of routes, or in more general environments, sequences of actions taken involving some objects. And these will be annotated with instructions from a person, and we'll train a model to map in one direction or in the other. So the current state-of-the-art models for this, like so many other things in NLP, are sequence-to-sequence models. So for a listener, you'll have a bidirectional LSTM encoder that represents your input instruction, and then you'll output your sequence of actions, one action at a time, using an LSTM decoder. And this will condition on a representation of this input instruction and also the current world context at each point in time. So a representation of the things that the agent can see from wherever it's at. And you'll produce these actions one at a time, so you have a probability distribution over action sequences conditioned on the context and the instruction. And this will be the base model that we build on later for other domains and for other inference procedures. So we'll also design a symmetric-based speaker model, which takes as input a sequence of actions along with the world context at the point where the action is taken and encodes it with a bidirectional LSTM, and then outputs the instruction one word at a time using an LSTM decoder that attends to the route. So we'll compare the different models that we have on two different data sets. So first is this really classic SAIL navigation data set that a lot of people have used in different work on semantic parsing coming from Ray Mooney's group. And so you have these examples that you've seen before of navigating in some kind of grid world environment with simple pieces of furniture in different parts of the world around you. So you'll show the model this instruction, you'll have it carry it out, and then you'll see the accuracy of was the final position that the model reached in the world the correct one that this instruction was supposed to guide it to. We'll also look at this more recent Scone data set, which has also been used for semantic parsing. And here there's three different domains, but this is an example of one of them called alchemy, where you have these different colored beakers and instructions for combining the beakers together, pouring them out. For example, remove all the purple chemical from the beaker on the far left, do the same with 1 unit of green chemical. So you have 5 of these different instructions. You start off with some configuration of objects, and then you try to carry out the instructions. And you're evaluated on accuracy of the final state. So here are 2 other domains from the Scone data set. You also have this tangrams domain where you have figures and instructions on how to remove them, add them back, and swap them around. And finally, this scene domain, where you have little colored figures and instructions on how to move them around or swap their hats and have them enter and exit the scene. So we'll evaluate these the sequence-to-sequence listener model on these tasks. And the accuracies are still pretty far below human accuracies on most of these domains. So people are a lot better at interpreting these instructions, but still not perfect. And in some of these domains where there's more specificity in the instructions, that it's easier for people, or it's easier for the model to pick up on than people, the model can achieve better performance. But in most of them, there's still a big gap in performance. And looking at some of the places where the model gets it wrong, we see examples like this one. So here you have an ambiguous instruction, like walk along the blue carpet and you pass two objects. And if we look at what the model did here, it produced a route that's a faithful interpretation of this instruction. So the model did walk along the blue carpet and pass two objects, and it stopped at this chair, which is a little bit farther than the second object. So this is going to be the core thing of the talk that we'll be focused on fixing. How do we understand that there's a better interpretation of this instruction than the one that this sequence-to-sequence model output? So we also have the speaker models, and we'll evaluate those by having the speaker produce a description of a route and showing that route, or showing that description to a person on Mechanical Turk and having them carry it out and seeing, did they get to the correct end state of the route that the speaker system was supposed to describe. So for this task, there's an even bigger gap in performance between the system and people on most domains. So this is the accuracy of people at carrying out the system's instructions. And particularly for these alchemy and scene domains, it's really hard for the system to output an instruction that a person can follow correctly in context. And looking at a failure case for one of these models, we see another issue with ambiguity. So here the base speaker model said, throw out the purple chemical. And that's a true description of what was done here. But if a person was trying to follow this, they would need to figure out which purple chemical was the model actually referring to. So it's just the context that makes this a bad description. The model hasn't learned that it needs to be more specific in this context. So next, we'll look at how a simple procedure for pragmatic inference, so reasoning about these different contexts, can be added on top of these existing models that'll fix many of these types of mistakes that we just saw. And we'll use this to improve both generation and interpretation. So let's come back to this example that we saw a little bit ago, where our system's given this ambiguous instruction to carry out. Walk along the blue carpet and you pass two objects. And if you think for a minute, how would you carry out this instruction? So there's this route, and this is the route that was intended by the person. So it walks along, it passes two objects, and then it stops immediately afterward. Whereas our base system was content to keep walking farther and stop at this couch, which is consistent with the instruction, but maybe not the best explanation of it. And we should have instead stopped immediately after passing the second object.
But the instruction did not actually say when to stop, right? It only said walk along.
That's right.
They were told when to stop.
Yeah, so both of these are consistent interpretations of the instruction. And so you kind of need to think about what would have made the person give the instruction that they did in order to figure out which one of these would be more likely. Sort of what was their reasoning process that caused them to produce this? Yeah.
So we have like what percentage of mistakes are like this, that they are consistent, versus the percentage of outputs that actually not even consistent?
So it's a fairly small percentage compared to model errors that are made. So we'll see some improvements from something that addresses this particular procedure. But yeah, it's a mix of both of those two types. So how should this listener agent carry out this instruction that it's been given? one way is to reason counterfactually about the person who gave the instruction, the speaker, which we'll show in orange here, and consider what routes might have made this person likely to give the instruction that they did. So this route that stops after just taking one step is not a good explanation of walk along the blue carpet and you pass two objects, because it's not consistent with that instruction. We didn't pass two objects. This one is a better explanation of the instruction, because we did walk along the blue carpet and pass two objects. But since this route continues on and stops at the chair, it would be better described in another way, like stop at the chair, or stop farther on, stop past the hallway. So finally, this route, out of all the ones that we've considered so far, it's the best explanation of the instruction that we've observed, which is kind of a marginal instruction, but it's best explained by this route. So this is the path that a listener that reasons about the speaker should choose to produce. So this sort of counterfactual reasoning procedure between a listener and a speaker might help us to resolve ambiguity in instructions, at least for cases like this. But we might think reasoning could also help for the inverse task of generating instructions. So we're shown this route as input. We want to produce an instruction that someone else could carry out to follow the route. So a very descriptive instruction might be go forward 4 segments to the intersection with the bare concrete hall. So it's specific about both how far to go and where to stop. And we can use reasoning for this task too. So here we have this speaker model in orange, and it's shown this route, and it needs to produce an instruction that a person would carry out with high probability to follow this route correctly. So something that has a high chance of getting them to the correct destination. And specifying how far to travel and where to stop could produce this effect in the listener. There's been a really long line on this sort of explicit pragmatic reasoning between speakers and listeners, but it's mostly been explored in pretty small domains, like interpreting expressions to choose between several discrete objects. So here someone said blue about these 3 objects, and you think, well, if they had meant the blue circle, they probably would have said circle instead. So I think that they probably meant the square. So it's a little bit of a contrived setting, and you place some constraints on the communication channel, but you get benefits from reasoning about why the person might have said what they did. People have also looked at this for generation tasks, again with discrete sets of reference. So here you want to produce a description that can distinguish between 2 different images. So you might choose to talk about something that's only in one of the images and not in the other, like the sun being in the sky. We'll apply these same kinds of reasoning procedures between speaker and listener, but we'll look at large and structured domains. So carrying out sequential actions in a complex environment. And in particular, we'll look at some real-world settings where there's ambiguity in the instructions and a difficult, like, visual perceptual problem to solve. So let's come back to this counterfactual reasoning procedure and think about how we would actually implement this with the models that we have. So we have this base speaker model, which we implemented as a standard sequence-to-sequence model. And this is going to take an input input route and produce a distribution over instructions describing that route. So we want to choose a route that's a good explanation of this instruction that we actually want to carry out. So we want to look at different possible inputs to the speaker model for a fixed output, which is this instruction that we want to follow, and then choose one that has a high chance of having made the speaker produce this given instruction. So to do this, we'll rely on our base listener model to propose some candidates for the base speaker to choose between. So this base listener model gets shown the instruction and then proposes a candidate set of routes, which are interpretations of this, each with varying probabilities under the listener model. And we can get these by using beam search in this sequence-to-sequence model, or sampling, or another inference method that we'll look at a little bit later on. We just need a candidate set that we can feed into the base speaker. And we show 2 here. In practice, we'll use 10 to 40 of these, but it's robust to the size once you get a sufficient number. So we'll take each of these candidate routes and we'll just re-rank them using this base speaker model. So this first route has a probability of 0.1 of making the base speaker produce this instruction, because this route would have been better described in some other way, like stop at the bench. So we assign that speaker probability to this route for the, and then we proceed on to the second one and get the probability for that under the speaker model, which in this case is higher, 0.2. So we choose that route as the output for this pragmatic listener model using the scores from the speaker model. So here's the graph that we saw before showing the accuracy of this base sequence-to-sequence listener model carrying out human instructions. And if we add in this pragmatic inference procedure, we see gains in some of the domains. And in particular, we see a benefit in this SAIL domain, where we get about a third of the way of the gap to human performance. And this kind of speaks to some of the ambiguity in these examples from the SAIL domain. So let's come back to our running example. So here, interpreting walk along the blue carpet and you pass two objects, the base listener made this mistake, whereas the pragmatic listener chooses to stop at this end destination that the person actually intended. If we look at an example in the scene domain from Scone, we'll see a similar effect. So here, the instruction is a red guy appears on the far left, then to orange's other side, but it's ambiguous about where the red guy should move on the other side of orange. So the base listener produces this kind of marginal but still valid interpretation, whereas the pragmatic listener moves the red figure directly next to orange, since next to blue would have been better described as to the left of blue or next to blue, for example. So it's sort of these kind of like hard, ambiguous edge cases that this pragmatic reasoning procedure helps for the listener. Yeah.
So it looks kind of like a Bayes rule. So instead of the probability of the meaning given the text, you're saying the probability of the text given the meaning, and normally there would be another term which would be the probability of the meaning. Like, is that a reasonable thing for them to have meant? Which you've kind of got in there in this proposal set. You know, you're kind of limited, but they're all sort of unranked. Is that a reasonable way to think about this?
Yeah, that's right. So I guess the way I've presented this, if you ignore the candidate set and you assume you were just choosing kind of uniformly from all routes, it would be like having a uniform prior over the routes. But we do constrain using the proposal distribution, which is maybe important because if you're kind of like feeding any route into this speaker model, which is just trained in this discriminative way, you could probably choose something that would just cause it to give high probability because it looks very different than anything it was trained on.
So are the numbers only the reverse probabilities from the base speakers rescore? Oh, it's a rescore. So you multiply both of those together.
So you can do both. You can use only the base speaker score. Something that works a little bit better is to just do a log linear combination of the base speaker scores and the base listener scores. So kind of like at the MT setup. Yeah. Particularly in the final domain that we'll look at, using just the base speaker scores does about as well as doing a combination of the two when you tune. Yeah, so we built this pragmatic listener that interprets an instruction by reasoning about a base speaker. And we relied on the base listener to propose some candidates for the speaker to choose from. To build a pragmatic speaker, we'll apply the same inference procedure and just reverse the roles of the listener and the speaker. So we'll propose a set of candidate instructions from our base speaker model and then choose the one that has the highest chance of making the listener modeled by this base listener do the correct thing. So as before, we have this base model, propose a set of candidates. So this time producing candidate instructions for this route that's input. And so here, the base speaker model is with higher probability going to produce an ambiguous instruction like walk forward past the stool, which is a true description of this route, but not the best one in terms of being likely to be interpreted correctly. But with lower probability, you might get something more specific like go forward 4 segments and stop at this particular location. So then we'll rescore with our listener model for this fixed output route that we want to tell someone to carry out. And this one will have a lower probability of making the base listener do the correct thing than this one. So we'll choose this one as the output for our pragmatic speaker model. So here's the figure we saw before, where these base sequence-to-sequence models pretty substantially underperform people in how easy are their directions to follow. But if we add in this really simple pragmatic re-ranking and inference procedure, we see really substantial gains so that we're comparable to human performance in a lot of these domains, and even get better directions that are more easy to interpret accurately in this tangrams domain. So it's important to evaluate these with by actually showing them to people and asking them to carry it out. You can look at automatic evaluation methods too, like we took a look at BLUE. As you might be able to imagine here, BLUE isn't a good predictor of whether direction can be followed or not, because there could just be one word missing that is the specifier that you need in order to carry something out correctly. So sometimes the pragmatic speaker produces gains in BLUE, sometimes it's worse, but this is totally uncorrelated with whether the instructions are actually followable by a person or not. So, yeah.
Do you have an intuition why the speaker results have so much of a gain as compared to the listener results?
So here, we'll see some examples where this base speaker model tends to produce things that are very ambiguous and that don't refer to context when it's necessary to refer to it. Whereas the directions that are produced by people tend to be unambiguous and kind of in most of the cases, we saw a few where they didn't do this, but in most of the cases are producing something that's specific enough that a model could condition on it to carry it out correctly. So sort of people know when you would need to say what you need to say in context, but the speaker models here haven't seen enough context to know when do I need to be more specific. So yeah, well, these examples kind of show that. So here the base speaker model says throw out the purple chemical, which would have been fine in another context if there weren't two of these purple chemicals. And maybe the speaker model didn't see enough examples where there were two of them and it needed to refer to the particular one that was necessary. Whereas the pragmatic speaker model correctly specifies that it's the first one that we should throw out. So this is within the support of this base speaker model. We get this by doing beam search in the speaker model, but it's not the highest scored one by the speaker model. We need the listener model to determine that this second one is more likely to be carried out correctly in context. And so here the human gave a very specific instruction that can be carried out correctly. Remove all the purple chemical from the beaker on the far left. So in one of these domains, in tangrams, we saw that the pragmatic speaker produced instructions that were easier for people to carry out than instructions produced by other people. And here's an example of that. So there's this final shape, the sailboat, that gets removed and then gets added back, but it's added back in a different position than where it was taken away from. So the base speaker model specifies the correct things, but doesn't say where the figure should be added. Whereas the pragmatic speaker says it should be added back in this third position. And actually the human made a mistake here too. So this was maybe someone working through Turk tasks pretty quickly and just said, undo the last step. It doesn't say that the sailboat should be added in a different position. So we see really large effects from reasoning about context for these generation models that need to do the right thing that's specific to the particular situation, if maybe the situation was different than what they saw during training. So we've seen that these base models that are trained on human data still have trouble with interpreting ambiguous instructions and sometimes generate instructions that are ambiguous in new contexts. But doing this explicit pragmatic reasoning between a speaker and a listener can help fix this. So finally, in this last part, we'll take these same techniques and apply them to a real world environment. So following instructions to navigate through houses and office buildings. And in this setting, directions are going to be harder to interpret because you have this really difficult visual grounding problem where there will be some objects that the model hasn't necessarily seen before that'll be referred to in the instructions, and you need to kind of anchor these instructions based on things that you do know and resolve the ambiguity that results. So we might expect pragmatics to help more in this domain for the follower. So the data set we'll be looking at came out really recently, and it's called room to room. So kind of like the sail hallway environments, it's a navigation task. But it's more difficult because it involves following instructions in these indoor environments like houses and offices. So people were shown paths like this one and asked to produce a route description. So here, turn left. And it doesn't say this, but you walk a little way. And take a right at the table, this table here. Take a left at the painting. And then take your first right. Wait next to the exercise equipment. So it's kind of an interesting domain because these are basically all show houses. So they're like really nice houses and they're all kind of nice in different ways. One of them is actually a palace. And I think the accuracy is lower on that one than on some of the others. But yeah, so the setup here is you have this discrete grid of locations in the environment, and each point is going to have a panoramic image that's associated with it that was taken from a camera at that position. And the listener agent needs to navigate around in this grid following the instruction and conditioning on the images that it sees along the way. So the vision makes this a challenging task, and directions can only refer to a small subset of this really rich environment that you see, and these objects might be difficult to identify, particularly if you're in a new environment. So this will lead to more ambiguity and a more difficult reasoning problem than some of the environments that we saw before. But the models that people have used for this task so far, which it's a new task, look really similar to the follower models that we used in the sail and scone environments. So actions will be produced sequentially using an LSTM decoder, which will condition on a representation of the instruction and the environment at your current position in the world. So here, your perceptual representation of the environment is the image that the agent can see based on where it's at and the direction that it's facing. And we'll summarize that using a really standard convolutional neural net that just feeds in a representation of this image to the decoder. So an action will be predicted at each time step, like move forward, and that'll update the agent's location in the world. And other possible actions are to rotate so that it's facing one of the other possible directions in the graph that it can go from this location, or to stop. And from this new location, it'll get a new image, condition on that, make another prediction, and so on, and eventually predict to stop. And at that point, it'll be evaluated on, was it close enough? Was it within 3 meters of the correct end location that this route was supposed to describe? So generalization is particularly hard in this setting because there's this really rich visual diversity. So there's 2 test conditions. In the first one, you have the same environments that you were trained on. So the same houses and office buildings, but you'll have different routes through those environments, of course, with different instructions for the routes too. But even though the model's been in this house before, it may be in a different location than it saw during training. And so it'll see objects from different perspectives or different objects. And you can train with exploration, doing like a dynamic oracle type thing that helps some with this. We'll build all of our approaches on top of this already existing exploration training. But even more difficult is if you're evaluating the model on unseen environments, where you may have a very different like style of furniture in this house, and the rooms will obviously be in a different configuration. So how will you deal with these objects that you've never seen before, maybe even different types of objects? So past work using this model on these 2 data sets sees much higher accuracies on these seen environments than on the unseen. And just to show you how difficult this generalization is, if you take a random baseline that at the start just picks a random orientation and then walks as close to straight in that direction as it can for a fixed number of steps, that gets pretty close to the performance of this sequence-to-sequence model on this data set. Again, with some caveats that this is, a pretty simple visual representation of the environment. But to try to improve generalization here, we'll use the same pragmatic listener that we outlined before and apply it on top of this existing base listener model. We'll build a base speaker model that is the generalization of the speaker models that we used before in the same way that the listener model is. So it'll just condition on this summarized visual representation at each point in time. And we'll talk a little bit about a technical issue that we have to solve in order to generate candidates effectively in this environment that results from the way that this model is trained with exploration. So in our base settings with the synthetic worlds, we could just do beam search and get a set of candidates that way. But we have to do a more structured inference procedure here. So before talking a little bit about that, let's abstract this inference procedure that the model needs to go through. So you have this direction that's given to you, and you'll produce a route one action at a time, which will give you a set of states in the environment that you're traversing. So you start off at A, and then you predict to move forward to the state B, predict to move forward to state C, and then stop afterward. And we'll use a structured search procedure to generate candidates in these environments that is going to be similar to using graph search with a closed list. So basically, in this navigation task, we're interested in the final state that we get to. And there will be some route through the environment that takes us to that state. If we just do standard inference, the model is pretty content to take routes that go through loops in this state space. And I can talk more about this later if you're interested, but it's an artifact of this training with exploration procedure. But we're interested in just the highest scoring route that gets to a state based on which state it's at rather than the number of steps that it's taken to get there. So we'll structure this inference procedure to keep track of the highest scoring route to each state and fill up this graph as we search through the space. So this will keep the space manageable. It'll just be linear in the number of states in our environment. And you can think of this as being like a beam search procedure where we have things compete based on states rather than number of time steps. So we start off with our initial state A, and we look at the possible candidates that we can go to from that state. So we can go either to B or to D, and we have a score for each of these routes that's parameterized by our follower model. So these are now the best ways to get to state B and to state D, so we store them in our graph. We next choose the highest scoring one that we haven't expanded yet, so A to B. And we'll get the extensions of that going to D or to C or stopping. So this route that ends at D now has a higher total probability than the past route that we found that goes to state D. So we'll replace that previous route with this better scoring one. And we'll allow this to refine our prediction of the best way to get to that state under this model. Same with C, that's now the best way to get to ending state C. And this route that is predicted to stop, we'll place in a list of completed routes that we'll build up and use as candidates for our speaker model. So we make those updates. We move on to state D, which is the highest scoring one. And the candidate extensions here go to states that we've already seen before, B and A, but have lower probability than the previous routes that we found there. So we just ignore those. And then this final route that we need to extend ends in C, and this predicts to stop or to go back to A, but it goes to A with lower probability, so we discard it and place C in this completed route set. And then we'll use this completed route set as the set of candidate lists for our speaker. So one thing to note here, I mean, this looks a lot like a graph search problem. But it's not a shortest path problem in the traditional sense because these edge probabilities are non-stationary. They depend on the past actions that you've taken to get to that state. And so you can't do a standard dynamic programming thing like Dijkstra's. This is just an approximate algorithm. It doesn't actually find the optimal routes to any of these states, but we find that it works decently well in practice. So we take these final set of candidate routes from our listener model, and we'll rescore them with our base speaker model and get the one that's the best explanation of this instruction that we want to carry out. So the same inference procedure that we used in the synthetic environments. So this pragmatic inference procedure helps pretty substantially in this domain of unseen environments. Training with exploration gets some gains in the seen environments, but not in the unseen, whereas considering multiple possible routes and feeding them into a speaker model to determine which one explains the instruction does increase performance. And as an example of that, so here's a route from the unseen environments. And the instruction here has some ambiguity both in the directions that it gives to objects that you might be able to recognize, but also maybe refers to some things that you haven't seen before. So the base follower model walks past the hall table, but the instruction doesn't specify which way to walk. And walk into bedroom. There's actually 3 bedrooms on this floor. And the base follower kind of heads towards this one, then changes its mind and backtracks into this other bedroom. The instruction says make a left at table clock. There's no table clock in this room, but the follower model is kind of already committed here and does the best that it can, waiting at this bathroom door threshold. Whereas this pragmatic model considers that route, but also considers this other one as a candidate, which walks into this other bedroom and makes a left at this table clock here, and then waits at the bathroom door threshold. And this was the correct route that the person giving the instruction had in mind. So we found that this pragmatic inference procedure lets us use the speaker model at evaluation time. If you have a set of candidate routes that you want to choose between, and choose one that's a good explanation of the instruction. But we might also imagine that a speaker model could help us at training time as well, to give us exposure to new routes through the environments with annotations for them. So this is kind of inspired by back translation in MT, where you have a set of monolingual text, and you'll train a model that goes from this target side text to a source, train a model in the opposite direction. So if we can get a set of new routes through our training environments, these are easy to produce because we have the training environments. We can just sample different start and end locations and get the route between them. So we'll have novel routes, and we'll annotate these routes with our speaker model, which is trained on the human annotated set of instructions. So for each of these synthesized sampled routes, we'll get an instruction produced by our speaker model, and we'll pair them up with the routes. And we'll use this as a synthetic training set and combine it with the original data set of human annotated routes, and take this entire combined data set and use it to train our base listener model. So it's a pretty classic semi-supervised learning setup. And if we stack this on top of this pragmatic inference procedure, so using the speaker model both at training time and at test time to select between routes, we see some further improvements even on these unseen environments. So the synthetic data here came all through the seen environments, but even though this is the case, we still see some improvements on different environments, which tells us that kind of seeing different complete routes with different language to annotate them, even if it's noisy language produced by our model, can be beneficial. So finally, just to bring this back to something that we saw before, we have this unified procedure for a pragmatic listener and a pragmatic speaker. And here we can build the pragmatic speaker by getting candidates and rescoring them using this listener model. So we haven't done human evaluations for this, but just kind of anecdotally, here's a route through a house with the human description, walk through the kitchen, go right into the living room and stop by the rug. And the base speaker model here produces an instruction that is kind of missing this key piece of information. It actually says wait by the table and chairs instead of stopping by the rug. while the pragmatic speaker here correctly specifies the location that the person should stop at. So we showed how using a single simple kind of re-ranking based inference procedure that's motivated pragmatically as a reasoning process between speakers and listeners can help improve performance on these real world kind of more practical tasks. So the listener here reasons about what might have made the speaker say this thing that they did, and then I'll use that to inform what I should do. And the speaker reasons about how the listener will interpret whatever the speaker says, and uses this to produce something that's the right thing in context. So pragmatics helps even on tasks that weren't designed as a test bed for pragmatic reasoning. And we found that it can help more even in these kind of real world domains where there's more ambiguity that we might expect reasoning to help us resolve. So thank you so much. And happy to answer questions.
Any questions?
Can you talk a little bit more about how you create synthetic data? Machine translation, we can easily mine monolingual data perhaps. For the routes, how do you make up the synthetic problem?
Yeah, so we generate this synthetic data by, you have this grid of environments, and if you choose a start location and an end location in that environment, construct the shortest path through the graph from start to end, and use that as your route. This is actually the same procedure that they use to construct the data set. So the data set takes that sampling procedure and then shows that route to a person and has them produce an instruction for it. We do the same thing, we just have the speaker model produce an instruction for the route. So it's kind of like, I mean, neither of these is naturally occurring, but they're both like synthetic in the same way. It's just that the human, I mean, the annotation is also synthetic here.
One thing that came up was that intuition why our gains over the base speaker is a lot more than our gains over the base listener. So please correct me if I'm wrong. But can it be that one reason why it might be the case is that basically our base listener performance, if the gap between the performance of the base listener and human performance is better than the gap between the base speaker performance and the human performance. So in a sense, the base listener is a better guide for the base speaker than the base speaker is for the base listener. And so the base listener is improving the base speaker better than the base speaker is improving the base listener.
Yeah, that's one way to look at it. I think there's also a difference in the input data that is coming in for the task. So if you look at this as a way to deal with ambiguity, either not producing ambiguous instructions or resolving ambiguity, the instructions that are given by people tend to be specific enough that in most of the cases, you could, it's pretty clear what you need to do. All the examples I showed here are ones where that's not the case, and you do get an improvement. So people are kind of good at saying the right thing in context. But the base models, like the base speaker model, I think is not. And so having this other model that chooses on top of it can help resolve that. So I think it's kind of like it helps you figure out how to generalize to context that you haven't seen before when that's necessary.
So this is great. You can automatically evaluate the listener, I guess, because are you 3 meters old, but you have to manually evaluate the generator, but by having someone try to follow the route. So in that second part evaluation, is there any worries about people in different groups trying to kind of compare systems? Everybody's hiring their own Turkers, and is there any worry about that, or is there a more systematic way where everyone knows to do the same thing?
So one nice thing is that the people who did previous work on generation released their code for the simulators. And so when we did these, we took the same code that they used with the mturk descriptions for it as well, and did the randomized thing where we showed instructions produced by their system showed instructions produced by our system and used the same setup as they did. So there was some difference in the scores of followability between like their study and our replication with their system outputs, but it was less of a difference than the difference between the pragmatic thing and the base thing.
So when you say 20 for them, that's your replication of theirs. What was their original for that?
So the only it was actually I don't think those results are not in this talk, but they're in the paper. People haven't done generation for scone before, and on SAIL they haven't done generation with one of these sequence-to-sequence models. They did a more structured thing based on templates. So we replicated their results, and the accuracies were similar to the scores that they got as well. And I think those were higher than our sequence-to-sequence, but lower than the pragmatic. Yeah, I should have had those results.
In some sense, like especially most of the examples you've talked about and worked on are those which where the human is not being very specific, and that causes ambiguity. And I guess would it be right to think that your work is trying to model assumptions that humans have when they're saying things like when they say cross two objects, they probably mean just that and don't do any more. Is an assumption that a human might have. Is that something that makes sense in that? What you're doing?
Yeah. If you have this this listener model that has a speaker model trained on human annotations, then it's in a way modeling what a person would tend to say for a particular situation. And so you're wanting something that's a good explanation of this instruction that the person produced according to your model of the person. So hopefully that's going to kind of capture the same assumptions that the person is making. It's kind of it's an interesting question why the base listener model isn't able to do that itself. So the listener model and the speaker model get trained on the same data from people, and the listener model is making these kinds of mistakes, and the speaker model is making these kinds of mistakes. But when we combine this inference procedure using the two of them, it corrects for it. So this is maybe kind of a more general thing, right? If you have some function that's predicting some state of the world and you bury that underneath some search, some inference procedure, that can kind of help you do better. You do more computation and then you're evaluating the world based on where you get to. It's just that the models here kind of haven't picked up that you need to, they haven't picked up that computation themselves. So doing the explicit search still helps.
It's funny because in the talk you mentioned at some point that maybe didn't see enough data to make that right conclusion. And now you mentioned that they both actually see the same data, but they're getting more out of that limited data.
Yeah. So both the listener and speaker see the same data, and I conjecture that if you saw more examples where you did see these two purple beakers, and it said the second in that case, then these models should learn to do that, unless there's some kind of fundamental limitation in the models themselves.
So in this case, you have a speaker model and listener model. They are two different models, right? And they have two different loss functions which are optimized separately.
Right.
So this is so much similar to machine translation. We have a foreign language model and English language model. So two different words, two different parallel words, and we are trying to find the mapping from one word to the other word. And maybe we could do the end-to-end optimization using cycle loss. Have you considered that approach where you go, instead of training two models, just optimize one loss function, which is a cycle loss function. You go from here to there, come back.
Do the round trip thing, and then you get the reward based on whether you recreated the original. Yeah, I think that would be really interesting. We haven't looked at that yet, in the same way that people have done with dual learning for MT or stuff like that. I mean, I guess in a way the synthetic data stuff kind of getting at that. You aren't doing joint training of the two, but you're at least trying to kind of compile the predictions of the speaker model down into your base model. But yeah, I think it'd be a really good idea to try doing this kind of round trip thing on this synthetic data. Maybe it would help more for the listener model than the speaker model, because kind of the language you're predicting maybe is going to not look like what people are saying. But yeah, you could do some setup where you could try to constrain that. Yeah, I think that'd be interesting.
Yeah, I was about to make the same comment about the dual learning because it looked like some similar. Another question is, when you combine the score of the primal model and the dual model, do you need to do any balance, or you directly combine the score?
So we take a linear combination of the log probabilities of the speaker and
do you
the
need
follower.
to tune that?
We tune that on a development set to maximize accuracy, or for the speaker to maximize blue, which there's problems with blue, but it's still better than not using a proxy. Yeah, for this navigation data set, you basically only need to use the speaker scores. You can just ignore the listener scores. So maybe the proposal distribution there is kind of peaked enough that just using this fixed set of candidates from the listener model gets you the same effect.
Oh, I see. You only use your primal model to generate candidate, and then you throw away the scores there.
We can do that. To get the best results, we use the scores from both. But we get almost the same accuracies. I think it's like 1 or 2% less on this task. This like real world navigation. On the synthetic ones, it's a larger difference in accuracy between using the combination and just using the speaker. But yeah, and for the pragmatic speaker, you can do well enough by only using the listener scores. But that kind of makes sense there because you're doing beam search, and so kind of everything you get is going to be high scoring since the vocab size is so large.
Is there any concept in these domains of a kind of a reasonable thing to ask the robot to do versus an unreasonable thing, so the robot would also just independently think, I'm not going to do that because that's an absurd interpretation of what I'm going to do this because that's something that needs to be done around the house or something like that. Is that possible to add into this? Or does these domains really not have that feature to it? It's all purple liquids it's all the same?
So yeah, so all the instructions that people have produced here are, unless they made a mistake, ones that you could actually carry out in the setting. So like people were shown the route and asked to give it.
That I understand, but of all those routes, let's say just the routes that, not the words, but the routes, they all maybe have a kind of reasonableness to them. Like you're going from one room, you're taking as opposed to going to one room and coming back and going to that room again and coming back. Could the robot use that sort of reasonableness criteria over the distribution of paths that people talk about?
Yeah.
To avoid. Do you ever see the robot doing something just bizarre and you go like, just on principle, it shouldn't have done that regardless of what the words were?
And like incorporate that using a prior or something. Yeah. So the routes here are always shortest paths through the environment. In this navigation data set. So they generated them by choosing a start and an end and getting the path between them. And so that's one reason why this inference procedure that gets the shortest path to each state, I think helps because it avoids loops in the environment. And we had, so I mean, that's kind of a way of at least like structuring your search to do something that looks a little bit like a prior over routes. But it'd be interesting to like model that more explicitly, I think, especially in these other, like the beaker mixing domains where I think they generated those from a grammar. And if you could like model that underlying grammar, it's baking more structure, more knowledge into the model, but maybe do better.
Any more questions? Thanks, our speaker again.
Thank you.